Electric field, that's what we're thinking about right now. And one word of warning before we start: field, force, they sound alike. They're easy to confuse as well. That you not only could end up saying field when you mean force, or force when you mean field. More troubling is when you think force when you should be thinking field, or think field when you should be thinking force. So stop, ask yourself, whenever you've thought of force or field, is that the correct thing that you should be thinking about? Is this question really about force, or is it about field? Don't just forge ahead unless you've answered that question. That sounds simplistic, but the number of people who make exactly that mistake is very large. Anyway, what is electric field? A good way to think about it is like this. Imagine a whole bunch of charged particles with all kinds of different charge, like 3 units of negative charge, or 2 units of positive charge, or a plane of positive charge. Then imagine another charged particle with positive charge. The textbook calls this the probe charge because it explores this area. The probe charge comes into this area where all these other charges are and lands at some location. We'll call that location X. And of course, it's going to feel a net force from the net result of the force from all of these other things. So there is a force on charge Q when it sits at point X. And here's where electric field comes into the picture. We can define electric field this way. As an equation, field at some point times the value of the charge that is sitting at that point will give you the force on the charge at that point. Okay, that's just kind of an algebraic statement, but what does electric field really mean? Electric field is the means whereby all of these charges can, so to speak, reach across space and apply a force to the charge Q. The way we think about electric field is that anytime we have charged objects, those charged objects fill the space around them, fill that space with something that we call electric field. And once there is electric field in this space, electric field at point X, for instance, then when a new charge comes into that region and lands at point X, it feels the electric field at that point. And it's really the electric field acting directly upon the charge. Sort of, it's the field that makes actual contact with charge Q. Then the field at this point making contact with the charge Q when charge Q lands here is what's responsible for the force on charge Q. Previously, we've been thinking about the force as coming, the force on a charged particle, like putting Q here at point X. The force comes from other charged objects. Now we look at it a little differently. We say that those charged objects that were already there before Q came into the picture, they fill the space around them with field, and then when Q lands here, it actually feels the field that was created by all these other things, and then feeling that field is what makes the force happen. It sounds a little weird, and at this point, it might stay sounding a little weird even after you've done the post video exercises, but the meaning and the usefulness of the field idea will become a little more clear in the coming days. So, as I've indicated here, field is a vector. So it's got a magnitude and a direction. And that magnitude and direction depend on the location. You'll have different fields of different magnitudes and different directions at different places. But let's think a little bit more specifically about magnitude and direction of field. First, direction. We imagine this charge to be a positive charge. What does that tell us? Well, if that's a positive charge, then what have we got here on the right-hand side? We're multiplying a positive number times a vector. Way back in earlier chapters, when vector algebra was explained, described, we were told that multiplying a vector times a plain old number, a scalar as we call them, gives us a new vector in the same direction as the old vector, e. The only difference between the new vector after you've multiplied by the scalar and the old vector is different magnitude. The magnitude of the new vector, q times e, is just q times the magnitude of e. Pretty simple. But the important point is, if this is a positive number, then this vector here has the same direction as this one. But now, this vector here on the right-hand side is equal to another vector, and for two vectors to be equal, they have to have the same magnitude and the same direction. So the direction of force is the same as the direction of this vector, but we just got finished saying that the direction of this vector is the same as the direction of field. So, to make a long story short, the direction of field is the same as the direction of the force on a positively charged particle. Let's write that out. The direction of the field at some point is the same as the direction of the force on a positively charged particle if you were to imagine putting a positively charged particle at that point. If you were to imagine putting a positively charged particle at that point, that if is important, because there's field at this point whether or not particle Q ever shows up at this location. Even if there's no particle at this location, there's still field at this point, because this point is in the neighborhood of all these other charges, and all these other charges fill the space around them with field. So there's field there, regardless of whether there's something else there or nothing else there, except field. And that field has a direction and a magnitude. Well, one other thing we can say, if the direction of field is the direction of the force on a positive charge, well, if we flip the sign of any charge, we flip the direction of the force that it feels. So a negatively charged particle has a force in the opposite direction from a positively charged particle. That's really what negative and positive mean. They feel forces in opposite directions. So we could say the direction of the field at E is the same as the direction of the force on a positive charge, if we put a positive charge at location X, or the direction of the field at x is opposite to the direction of the force on a negative charge, because this, the force on a positive charge, is opposite to the direction of the force on a negative charge. That's worth writing up too. The direction of an electric field at some point, call it x, is opposite to the direction of the force on a negatively charged particle if you were to put a negatively charged particle at that point that we're calling x. And let me rewrite this for just a second. This equation here actually works. It's true whether Q is positive or negative. If Q is positive, then multiplying a positive number times a vector gives us a new vector in the same direction. But of course, if Q is negative, negative number times a vector, that gives us a new vector pointing in the opposite direction. So if Q is negative, then this vector, Q times field, will be in the direction opposite to the electric field itself. Multiplying a negative number times a vector flips the direction of the vector around. So this direction, the direction of this vector, if Q is negative, is opposite to the direction of the field. So this vector must point opposite to the direction of the field. If Q is negative, this vector points opposite to the direction of the field. That's direction. What about magnitude? The magnitude of an electric field depends on exactly what the source of that electric field is, one charged particle or many charged particles. Let's just look at the simplest possible case, an electric field caused by just one charged object. So the book usually calls the charge that is the source of a field Q prime, so I'll do that too. And so here's some charged particle, Q prime. Being a charged particle, it does what every charged particle does, creates a field in the space around it. So go out some distance d away from that charged particle, and there is field right here. And of course, field at that point, of course, the direction of the field at that point would be the direction of the force that a positive charge would feel if you put a positive charge there. You put a positive charge here, well, if Q prime is negative, then you've got two positive charges. They apply repelling forces to each other, so in that case, a positive charge here would be repelled by Q prime. So this would be the direction of the force on a positive charge here. So this would be the direction of the electric field if Q prime were positive. And then, as you might expect, if Q prime were negative, the field would point in exactly the opposite direction. Imagine putting a positive charge here. Imagine that Q prime is negative. Now you've got a negative and a positive charge. Opposite charges, they attract each other. So the positive charge here is attracted by Q prime. It's pulled toward Q prime. So if Q prime is negative, the force that a positive charge here would feel is a force that way. And since that's the direction of the force on a positive charge here, if Q prime is negative, then that's the direction of the electric field at this point, if Q prime is negative. Okay, now, magnitude of field, well, go back to our rule and rewrite it a little bit. We can write it as electric field at point X equals the force on our charge Q divided by charge Q, and Q is at point X. We're looking at just the magnitude of the field, so we want just the magnitude of the field. If this vector is equal to this vector, then the magnitude of this vector must be equal to the magnitude of this vector. So we can say that. And what we have in this case is just one, we're imagining one particle here at point X and just one other particle. Whenever two charges are interacting with each other, we know how that works. Coulomb's law tells us how that works. Coulomb's law is the equation that we use to figure out what this force is. So let's write that out. That force is equal to that K constant times the absolute value of the source charge times the absolute value of the thing that's feeling the charge divided by square of the distance between Q and Q prime, all divided by the magnitude of Q itself, the probe charge, the charge that you're imagining putting at point X. Well, here's an absolute value of Q, and here's another absolute value of Q in the denominator, so they cancel each other out. And all we're left with for the electric field caused by a charge Q prime is that that's the magnitude of the electric field caused by Q prime. Which is K. The K constant is a positive number, times the absolute value of the source charge, the other charge canceled out, divided by d squared. So at any point a distance d meters away from the source charge, that's the field strength. And notice one important thing, the field depends on the source only. It doesn't have anything to do with the Q charge that is feeling the field and the force. Now, if we keep the source charge the same and then just look at different points in the neighborhood of Q prime, the source charge, then the numerator is constant and the square of the distance, of course, varies. Now we've got an inverse proportionality, and it's the same inverse proportionality that we had when we were talking about Coulomb's law. The magnitude of the field is proportional to 1 over distance squared, or inversely proportional to distance squared. Remember, inverse proportionality means when one thing increases, the other variable that it's proportional to decreases. So if d increases, you get farther and farther away from Q prime. If d increases, field decreases. That's the same kind of thing that we see in electric force. As you get farther and farther away from the source of a field or the source of a force, the field or force get weaker. And specifically, because it's d squared. Remember what we had when we talked about force. Say you've got one distance, and then you're at one distance from q prime, the source of the field, and then you move twice as far away. So your new distance is twice the old distance. The thing that magnitude of field is inversely proportional to is d squared. So that means that we must figure out how d squared changes, not just how d changes. Square this whole equation to find that out. d2 squared equals the square of this, 4 times the square of this, d1 squared. So the variable called distance squared changed by a factor of 4 when the actual distance itself doubled. So d squared changes by a factor of 4. Anything that it's inversely proportional to changes by the inverse factor, 1/4. So field gets weaker, gets cut down to just 1/4 of its original size. Same thing that we saw when talking about electric force. You move the two particles twice as far apart, then the force they feel is 1/4 as strong as it was before. Let's look at a couple examples of that. Okay. Let's say we have two charges, both the same amount and both positive, and then we're looking at 2 points. One point here right in the middle between those two charges, and then another point 2 over here. To keep things simple, let's say all of these spacings are equal. And we want to compare the strength of the electric field here to the strength of the electric field here. Well, the electric field here, electric field at point 1, is a net electric field. It's a sum of the electric field that this one causes plus the electric field that this charge causes. And just so to make it easier to talk about these things, I'll just label them as charge A and charge B. So the net field here is just the sum of the field caused by charge A plus the field caused by charge B. Okay, what is the net field there at point 1 like? Do the same thing that I did when talking about net force on a charged particle when it feels forces coming from more than one other particle. First, think about directions. What's the direction of the force? What's the direction of the field at point 1 from charge A? Well, field points in the direction of the force on a positive charge if you had put a positive charge there. So imagine putting a positive charge here. What kind of a force does it feel from charge A? Positive here, they're both repelling forces. So this feels a repelling force. It's pushed away, a positive charge here would be pushed away from A. So a positive charge here would feel a force to the right. We'll call that the positive direction. And that is negative, so whatever the magnitude of that field is, it points in the positive direction because put a positive charge here, it would feel a force in the positive direction. And now, what about the field caused by this one? Put a positive charge here, sees positive charge B, so there are repulsive forces because they're the same type of charge. That is, the charge here gets pushed away by the force that comes from B. So the force on a positive charge at point 1 caused by B would be a repelling force, which means the charge at 1 gets pushed to the left. That's the negative direction of the force, and that's the negative direction. It's the direction of the force on a positive charge. Direction of the field is the same as the direction of the force on a positive charge. Okay, so now we don't have enough information here, obviously, to get numbers, but we can say something about relative sizes of field strengths. And let's just define, like we did in the case of force, sort of a basic unit of field. We'll say that 1 unit of charge, if you go just 1 step away from that charge, creates an electric field at that point whose magnitude we'll call just plain E. And so A is 1 unit of charge 1 step away from this point. So the force at this point caused by A is just E in magnitude. Likewise, B, charge B, is 1 step away, is 1 unit of charge 1 step away from point 1. So charge B also creates a field at 1 with a magnitude of just plain E, 1 unit of charge 1 step away. And of course, E minus E, 0. The net electric field at point 1 is 0. In other words, if you actually put a charged particle at point 1, it feels no net force because there is no field there. And you have to have field in order to have force. That's what this rule means. If you have no field at point X, E is 0, then the force on a particle at point X is 0. Okay, let's now think about the electric field at point 2. It again is a net electric field. It's the sum of the electric field caused by charge A plus the electric field caused by charge B. Caused by A plus field caused by B. And again, let's start with directions. Imagine putting a positive charge here at point 2. This is a positive charge also, so a positive charge here would feel a repelling force from charge A. The force on a positive charge at 2 caused by charge A is a repelling force pushing the positive charge here away from A. In other words, it's a force in the right-hand direction, so the field points to the right, because field at this point would point in the same direction as the force on a positive charge. So that's a positive charge. And then you could say exactly the same thing about this. Put a positive charge here. It sees positive charge B. So a positive charge here is repelled away from B. The force on a positive charge here is a push to the right. So at this point, the force on a positive charge, the force caused by B on a positive charge here, is a rightward force. So the electric field at this point, that is the field caused by B at this point, is also a rightward force. Field points in the same direction as the force on a positive charge. So they're both rightward forces. They're not in opposite directions, so they're not going to cancel out this time. You're not going to come up with a net field of 0. Well, we can say one thing very easily right away. Just like when we were thinking about point 1, from point 2's perspective, charge B is 1 unit of charge 1 step away. So 1 unit of charge 1 step away causes a field 1 step away of strength that we call plain old E. So the magnitude of B's field at point 2, the magnitude of the field caused by B at point 2 is plain old E. And A will be a weaker field because it's farther away than B. How much farther away? Well, B was 1 step away. A is 1, 2, 3 steps away. How does that reduce the strength of the field caused by A? Well, remember, field caused by just one charged particle is K magnitude of the source charge divided by distance squared. Well, as we shift our attention from the field caused by B to the field caused by A, the distance from A, from charge A as source of a field, distance from A to point 2 is 3 times the distance from B to point 2. Then field strength depends on d squared, not d, so we have to square this equation to actually see what's going on. D squared A is 9 dB squared. So as we go from thinking about the force at 2, or the field at 2 caused by B, to the field at 2 caused by A, the denominator here gets 9 times bigger. So the field strength is only 1/9 of the field strength for A. Field strength caused by A is only 1/9 of the field strength caused by B. So this is 1/9 E. Plain old E was our name for the field strength caused by B at point 2. So the net field at point 2 is not 0. It's 10/9 times 10/9 times the field strength you would get from just 1 unit of source charge 1 step away. In other words, just a tiny little bit bigger than the field you would get from charge B alone. Okay, now one last example. Let's think about 3 particles causing some electric field here at point X. And so the electric field at X is a net field, and it's call these left, center, and right charges. It's equal to the field at X caused by the left charge plus the field at X caused by the center charge plus the field at X caused by the right charge. And do as we did before, first think about directions and then we'll think about magnitudes. Put a positive charge here. It sees this positive charge, and since they're both the same type of charge, this is repelled away from this one. In other words, this feels a force. Put a positive charge here and it'll feel a force that pushes to the right. So here, force from this thing is a force that points to the right. So here, field from this thing points to the right. The field at this point caused by the left-hand charge points to the right. Now here, what about the field caused by the C charge? put a positive charge here, it sees this negative charge, which is which makes an attracting force. A positive charge here is attracted towards, pulled towards negative charge C. So put a positive charge here, the force that it feels from C is a rightward force. Therefore, at this point, the field caused by C is a rightward field, also positive direction. And then finally, the field at X caused by the right-hand charge, imagine putting a positive charge here. It feels a repulsion from this. That is, a positive charge here would feel a repelling force from this, and being a repelling force, it would push a positive charge to the left in the negative direction. So, the force that has this charge as its source and acts on a positive charge here would be a leftward or negative force. Therefore, the field that is caused by, the field at this point that is caused by this charge is a leftward negative field. So there we are. Now, magnitudes. This charge is 1 unit of charge 1 step away from the point that we're looking at, so that creates a field strength of what we call plain old E at this point. This is 1 unit of charge 1 step away from this point, so this would also create a field with strength of plain old E. This is 2 steps away, so at first we think about the field due to C, then the field due to charge R. We've doubled the distance. This is 1 step away, and this is 2 steps away. So doubling the distance cuts the field down to 1/4. The field here, caused by this one, is only 1/4 as strong as the field at X caused by this, or the field at X caused by this. So then the final result here is 7/4 E, and plus 7/4 E. That is, the net field points in the positive direction. The net field at point X is a rightward field, and the magnitude of that field at point X is almost twice the strength of the field that we would get from just 1 charge 1 step away. Okay, and at this point we're just getting used to thinking about field. It's not easy to think about, and like I said, be patient. The actual significance and usefulness of field we see later on. At this point, it really doesn't look like the concept of field adds anything that we don't already know by thinking about forces. But we will see, like I've reassured you several times, we will see that actually the concept of field does add in some important new ideas.